Okay. So let me remind you exactly where we were last time. We had defined this class called NP, right? NP essentially is characterized as follows. So a problem is an NP if one, it is a decision problem. And 2, it is verifiable in polynomial time. So before we get into things, any questions about the way we have been going about this particular topic? Do you understand what it means to be verifiable as opposed to solvable? How many here still do not understand what I mean by verifiable? Okay. So essentially, there are some problems that are solvable in polynomial time. Okay, I give you the problem, and you find a way of taking that problem and solving it in polynomial time. The basic idea behind verifiable comes because there are problems out there that we have found to be very difficult to solve in polynomial time. Every algorithm that we come up with, it looks like is going to take us exponential time. Okay, that's essentially the background from which this verifiability notion is coming. So essentially, we tell ourselves that, hey, if somebody were to make the problem much easier than it already is, could we still do something in polynomial time? So rather than find a witness or a certificate and then say, well, this is the best I could do, and here is a threshold based on which I will give an answer yes or no. So this lies below the threshold, and therefore I will give the answer yes. If the solution for mine had turned out to be here, I would have said no. This is the problem we are having great difficulty with. So we ask ourselves a simpler question, that if somebody were to give us this certificate, could we at least look at that certificate and say whether it's lying here or lying there? Because if we cannot do that, then solving the original problem is outside our capacity to do in polynomial time. If you cannot even verify a solution in polynomial time, how do you expect to solve the problem in polynomial time? The assumption would be that maybe your algorithm would first of all look for some kind of a certificate, solve for it, and then do the verification. Of course, there is no necessity for that, but one way to solve this problem would be to first go around, look for the certificate, and then check the certificate. A very simple example would be, given a graph and a u and v, is there a path from u to v that is less than or equal to k hops? The way we would solve this problem, and we know that we have a polynomial time solution to this problem, is first of all do a shortest path, produce the shortest path, that would be our certificate, and then just check and see whether the shortest path turned out to be less than or greater than that k that has been given to you. So that is the mindset essentially. Okay? If you cannot solve a problem in polynomial time, we believe that, if you cannot verify a problem in polynomial time, then we believe that it is very unlikely that you would solve the problem in polynomial. Okay, so that's the notion of verifiability. We are loosening the requirement essentially, because we are not being able to solve some of these problems, and I'll show you those problems out there. Does that make any more sense than before? How many say yes? Okay, good. Okay, so in the class NP, the problems that are verifiable in polynomial time, there is nothing here that says that but is not solvable in polynomial time. There is no necessity for it. So what we are saying is that this class is rather large, and there are some problems that are easy in it. These are the problems that are solvable in polynomial time. Now, if this class turns out to be the entire class, then it would mean that any problem verifiable in polynomial time is also solvable in polynomial time. That we do not know. We do not know the answer to that. However, we know, based on the proof I gave you last time, that if it is solvable in polynomial time, then of course it's verifiable in polynomial time. That is why we said that P was a subset of it. Okay. So, we are looking at this landscape and we are asking, can we pick out certain problems from this which we think are hard. And the way we went about looking for hardness is something called NP hard. So, here is the class NP hard, and the reason it is sitting outside of NP is that there is no requirement for an NP hard problem to be in NP in the first place. So, you can have optimization problems sitting out here which do not belong to NP. Okay. It is a very simple thing. So, the core aspect is the hardness of it, but unfortunately, we are not restricting them to be in NP. And so, this set which are in NP and are NP hard, this is what we call NP complete. And just like that, it is very difficult to say that there would even be a single problem there which is NP complete. So, what we did last time was essentially tell you that Cook actually found one problem that is NP complete, by which we mean what he showed was that every problem in NP is reducible to the Boolean circuit satisfiability problem. Every problem in NP. So, you choose any problem in NP, let us call it L, and let us call Boolean circuit satisfiability problem to be B. What he showed was L is reducible in polynomial time to this problem B. The implication of this is the following. If it turns out that you can solve this problem in polynomial time, you would essentially be able to solve all problems here in polynomial time. The reason for that is that when I give you this problem, you would first reduce it to this problem, you would solve it in polynomial time, and you would give me the answer. And therefore, you would have a polynomial time solution to this. The flip side of this is that we believe that these problems are extremely difficult to solve, because if we did solve this problem in polynomial time, we would have then the implication would be that P is NP. If this has a polytime solution. Do you understand what the argument I am making? If I can show you that any problem in NP is reducible in polynomial time to the Boolean circuit satisfiability problem, then what I have essentially shown you is that any problem in NP can be solved in polynomial time, not just verified, because every problem in NP by definition can be verified in polynomial time. Okay. What I am going to do is I am going to take a slightly non-orthodox route to this area. I will not try to prove this for you, because this proof is more difficult than the other examples that I can show you. So, what I am going to do is I am going to jump ahead, do a couple of proofs, and then I will come back to this proof. Okay. So, for now, just believe me, or rather believe Cook, that he has shown you one problem that is NP complete, NP hard and in NP. I will show you that based on that we can show other problems are NP complete. And it turns out that soon as Cook finds this one out, and it was around the same time that Richard COT was also working on similar problem. So, in one short year we found many problems that are NP complete. Cook showed that this problem was NP complete, and Richard COT through many of his reductions showed that if that problem is NP complete, then these other problems are also NP complete. Okay, so, I will do those first. I will then step back to this main thing. Okay, so, your goal now is to not be very satisfied, just accept the fact that Boolean circuit satisfiability is NP complete. Let us go ahead and show that there are other problems then, that are also NP complete. We can come back to the Boolean circuit satisfiability problem being NP complete later. Make sense? Okay. So, the assumption now, so what we will show is that this other problem then is NP complete, and this other problem is called 3-SAT. SAT stands for satisfiability. 3-SAT is actually, the full form is 3CNF SAT, but we essentially drop the CNF because it is understood that it's a CNF. Okay, and let me tell you exactly what this thing is. A CNF stands for a conjunctive normal form. What is a conjunctive normal form? Well, it has a bunch of clauses which are attached to each other using ANDs. Okay, for those of you who have done architecture, you probably already know about CNF, but those who haven't, we can just quickly go through the definition of CNF. So, you are going to have a bunch of clauses, and that are going to be attached using ANDs. And inside each clause, you will have something called literals. And literals are either variables themselves or not of some variables. These are the only things that are allowed. So, you have variables or not of variables. So, and the way these things are connected has to be with ORs. Okay, so that is a conjunctive normal form. It's a very structured way of writing Boolean formulas where you have clauses attached with ANDs, and each clause has only ORs and NOTs. This is a standard conjunctive normal form where you can have as many literals in your clauses as possible. When we say it is a 3 conjunctive normal form, we are only allowed exactly 3. Okay, so, this will look something like, say that. You will have 3 literals per clause and some number of clauses. What we are trying to show is once again that these problems also are extremely difficult to solve. And the way we go about showing it is that we prove that this is NP complete. And to prove that it is NP complete, we have to do 2 things. One is that we have to show that it is in NP, and second, we have to show that it's NP hard, by which we mean we have to show that every problem in NP can be reduced to that problem. That's a very tough thing to do, except that we now have Cook come and help us. So, what we can do then is the following. You have all the problems in NP reducible to Boolean circuit satisfiability in polynomial time. If I can show you that the Boolean circuit satisfiability can be reduced in polynomial time to 3CNF, then through this double jump, I have just shown you that all problems in NP are in polynomial time reducible to 3CNF. And the reason for that is that a polynomial of a polynomial is a polynomial. So, if the first transformation is through a polynomial and the second transformation is through another polynomial, the whole transformation can be seen as a polynomial. So, essentially what we are doing is that we are using Cook's theorem to show that everybody is reducible in polynomial time to 3CNF. Is that argument making sense? The usual problem, you need to draw this picture in your head constantly, because the place I see people making mistakes is that when they are trying to show that 3-SAT is NP complete, or in this part NP hard, they end up showing the following. But this is just one piece of Cook's theorem itself. Cook has shown that every problem is reducible to Boolean circuit satisfiability. You are coming and showing me that one of them is also reducible to the Boolean circuit satisfiability problem. It's not helping me at all. You are a small piece of Cook. So this is the wrong thing to show. Okay, I want you to get this into your head, because it turns out that this is one of the big problems people face. Finding out which problem has to be reduced to which problem. Draw this picture in your head. Always draw this. Remind yourself that this is Cook. And then if you have to show that everybody can be reduced to your problem, you have to show Cook or binary Boolean circuit satisfiability can be reduced. Making sense? Okay. So this is the piece that we want to show. That is a piece that will tell us that the 3CNF is NP hard, but before that we have to show that 3CNF is in NP, the easier part. How would you go about showing 3CNF is in NP? One, is it a decision problem? I give you a formula. The 3CNF problem is that when this formula is given to you, you have to come back and say whether it is satisfiable or not, whether there is some assignment to the variables in the clauses that makes the whole formula true. And you can clearly see, because the formula has a lot of ands in it and only ands are allowed, you need a assignment to these variables which make each one of this true. That is what makes this problem extremely difficult. But right now we are not trying to solve the problem. Remind yourself that when we are playing with these things, we are never trying to solve these problems. We are just turning one problem into another and so on and so forth. Because we have tried for the longest time to solve this problem. We haven't succeeded. So we are trying to explore and see why is it that these problems are difficult. Are there other problems that are also difficult, and so on and so forth. So we have to show that 3CNF is in NP. One, it's very clearly a decision problem. The answer is always yes, it is satisfiable, or no, it is not. The slightly more difficult part is to show that it's verifiable in polynomial time. For that, you just need to show me what your certificate is going to be and how you are going to go about verifying that that certificate satisfies this. So what is your certificate going to be? Somebody else? What is, yes? The set of assignments. Okay? So you just take each literal and you assign it a certain truth value. Now, in order to verify, you have to make sure a couple of things. One is that you have not said not x1 is going to be true someplace and then x1 is going to be true someplace else. You have to verify that. Once you have verified all of those, then you know that each variable has been assigned a truth value. You can then go clause to clause to clause to clause and just make sure that in each clause there is at least one literal that is true, because these are all ORs in there. That again is going to take you polynomial time. You can clearly see I am not writing a very complicated algorithm for you. When you are asked to solve these problems, just speak it out in English. We will know whether you are giving me a polynomial time verification algorithm or whether you are giving me an exponential time verification algorithm. In this particular case, you are just going from left to right. It is essentially linear. So you don't have to write it out in for loops and so on and so forth. You can just declare that I have done it from left to right. It is linear to verify this, and therefore this is a polynomial time verification algorithm. Okay? Okay. So that takes care of the easy part. The second part is the one which is difficult. And to show 3 CNF is NP hard, we will prove that the Boolean circuit satisfiability problem is in polynomial time reducible to 3 CNF. Okay. And here again, I am going to describe it to you picture wise. I am not going to describe to you the exact algorithm, because once you understand what is happening, you will be able to write this algorithm down for yourself. So, assume that you are given a Boolean circuit satisfiability problem. It probably looks something like that. So, you have a bunch of guys here, some OR gate, maybe another NOT gate, an AND gate, and so on and so forth. Okay. What I am going to try to do is take this and turn it into something that looks like that. That is what it means to be able to reduce a problem. You give me a problem in your domain, I will turn it into a problem in my domain. So, when you give me any circuit in the Boolean circuit satisfiability problem, I need to take that problem and say, for this I am going to produce you another problem. This is going to lie in the 3 CNF satisfiability domain, and the important thing I need to show you is that if the answer here is satisfiable, the answer there is satisfiable. And if the answer here is not satisfiable, the answer there is not satisfiable. And the way I do this transformation has to be in polynomial time. These are the requirements. Okay? This is probably the easiest one that we can target. I will show you very soon that you can jump domains. In this particular case, you can clearly tell that this is also about satisfiability, that is also about satisfiability. It is probably not going to be very difficult to crack this one. So, the first thing I do is I essentially go to each gate and make sure that it does not have 3 or 4 or 5 input leads. I am going to make sure that it only has 2 input leads. Okay. So, I am going to take this, and so if you have 3 going into an OR, I can essentially make that something like that. Okay. So, 2 by 2 by 2. Very clearly, there are n input lines. So, by doing this expansion over the entire network, I am not going to end up producing an expanded version which is exponentially large. Can you argue that in your head? Because I am going to take only n, and each gate can at most be extended n times, and that too is it's actually extended n minus 1 times, because if you have n leads, I just want it brought back to 2 leads. So, each gate can become n times. The entire circuit will just multiply by n. That is also, if it was previously a polynomial in n, the circuit depth and the size, if it were say 3n squared, then multiplying with that with n is giving me 3n cube. It is also a polynomial. Okay, so, that is the first piece. So, I am going to take this and I am going to expand it out so that each lead has now just 2 inputs coming to it. Now, I am going to do the following. Let us assume that I have done this already and I have just 2 leads going in everywhere. Mind you, I am not trying to solve this problem. I am trying to turn this into that problem, and I want to do it in such a manner which is polynomial in time. If I start playing games with this to try to turn it into a 3 CNF, and that game essentially takes me exponential amount of time, the game is lost. I want to be very careful, not trying to solve this problem and yet turn it into a problem of that kind. Okay. All I need to make sure is that they are equivalent. And in this particular case, it takes only a little bit of thought, creativity to do that. What we do is we take every output and assign it a new variable. So, if you have x1, x2, x3, I will make this x4, I will make this x5, I will make this x6. Okay, I am going to assign to each lead coming out of any place a new variable, And then I am going to write this whole thing down in the form of a bunch of ANDs. So, I am going to claim that this circuit is equivalent to saying that x4 is equivalent to not x1 and x5 is equivalent to x4 or x2 and x6 is equivalent to, well, I am sorry, I did not put, make that 7, make this x6. So, we have x6 is not equivalent to not x3 and finally, x7 is equivalent to x5 and x6 and finally, x7 is true. So, this thing is satisfiable, corresponds to this formula is satisfiable. This is the creative jump. In all NP hard problems, when you are asked to show something is NP hard, you have to pull out by magic from your head this transformation. I have taken a problem here and I have written it which looks halfway like a 3CNF. All that remains is to take each piece here and turn those into something that fits the definition of 3CNF. How many think they can do this? Because remember, I have already produced a bunch of pieces which are all attached with ANDs. I now want to take each one of these and turn them into something that fits the 3CNF model. It might not be obvious to you, so let me just show you what I am going to do. Let us take one with 3 variables. Okay? The ones with 2 variables, I am going to throw in a dummy variable to make it 3. We will only have essentially 2 here and a 1 here, or a 1 here and a 1 here. So, we will have 2's and 3's. The 3's I will show you how to do, the 2's you have to throw in an extra dummy variable. The 3's I am going to do in the following manner. So, I am going to take x5, x4 and x2 and give them all possible ways they can go about it. So, you can have 0, 0, 0, 0, 0, 1, 0, 1, 0, there are 8 of those. I then go row by row by row and I ask whether this thing is true or not. So, in the first row you have x5 is 0, x4 and x2 is 0. If these two are 0, the OR is a 0, 0, 0. Okay, so, that is a true. This formula is satisfied here. You go to the next one, x4 and x2, one of them is a 1. So, this becomes a 1, but this is a 0, this is not satisfied, and so on and so forth. So, this formula is essentially equivalent to the places that these things are 1. So, it essentially says either x5 is 0 and x4 is 0 and x2 is 0, or, and then you go to the next line, or you go to the next line and so on and so forth. But if you wrote that, then it has a bunch of things attached with ORs. I want just the opposite. I want a bunch of things that are attached with ANDs. What do I do? Use De Morgan's law. What I will do is I will check for the places where there are zeros. I will say it is not the case that x5 is 0 and x4 is 0 and x2 is 1. In other words, not the case that not x5, not x4, x2 or something and so on and so forth, but the not is sitting outside, and when I send the not in, the ORs will become ANDs, the not will go in, and those ANDs inside the clause will all become ORs. Perfect. I push the not in, the ORs between the clauses become ANDs. I push the knot in even more, the ANDs within the clauses become ORs. Each one of these will then have a certain size, and you can essentially guarantee the largest number of clauses you will produce for one of these classes. It is essentially about turning each one of these into a 3CNF. Plug them all in, you will get another one, it is polynomial in size. We have just done the transformation. And because we did the transformation in a way where we kept the equivalence to be the case at all times, we now know that this circuit is equivalent to that 3CNF that I just produced. I have therefore shown you that 3CNF is NP high. And because I showed you that 3CNF is NP complete before, sorry, in NP before, I have proved to you that 3CNF is NP complete. What this means, once again, what this means is that 3CNF is again one of those problems where every problem in NP can be reduced to 3CNF. Very likely 3CNF is very difficult to solve. Yeah.
Inside each clause, we may have more than three ANDs.
We will never have more than 3 ANDs inside each class, simply because I took this first step where I took every gate and I said if you have many leads, reduce it to 2. So, there will be just 2 of these and somebody on the other side, right. Now, your question might simply be that when I take this and I open it up using a 3CNF, it might have more than some number of clauses. All you need to do is give me a bound, a constant bound. How many clauses at most? I can immediately tell you at most 8 clauses. You see, there are only 8 rows. There are at most 8 clauses per clause here. So, you just multiplied it with a constant that remains polynomial in size. No, 3SAT is any number of clauses with 3 literals. Well, if there were only 3 clauses, it would actually be very easy to solve. It is any number of clauses, but each clause has only 3 literals. Did this reduction make sense? This is the easiest possible reduction. If this does not make sense to you, it is unlikely that you will be able to do any other reductions. Of all the reductions out there, this is the easiest one. Yes? Are you sure? Okay, but 2 power 10 is still a constant. See, the 10 is a constant. That does not matter. It cannot grow in the size of the problem. Yeah, a 3SAT, the problem size is not the 3 in it. It is how many clauses, how long it takes you to write the whole thing. That is the size of your problem. Okay, there is this big difference between the constants. It is true that finding, like I said, a 10 clause version of 3SAT, that is a simple problem. It is the variability of that guy that is what is a problem. Right? From very early on, we have been trying to do complexity analysis where we do not say you are given an array of 10 elements. There is no complexity analysis there. It takes a certain amount of time. We do not care how much ever it takes. It is as the size of the array goes up, does it take polynomial, does it take n log n, does it take n squared? That is where complexity analysis comes in. So, in this case, the 3SAT, the 3 stands for not the number of clauses. It comes from the number of literals that are allowed in each clause. The number of clauses are variable. That is where the openness of the problem is. Any other questions? Yes. If you go about this, you might have you might have very little difficulty to do that. In fact, Cook's theorem says anything can be reduced to the Boolean circuit satisfiability problem. So, you are showing a small piece of Cook's theorem then. Okay? That is the mistake many people make. They make the reduction the wrong way. If you reduce the wrong way, you haven't shown anything. You have just shown a small piece of Cook's theorem. Cook has shown that any problem in NP can be reduced to Boolean circuit satisfiability. You are showing that this particular problem is reducible to circuit satisfiability. Well, big deal. Cook has shown any problem can be done. Remind yourself of that, because that messes the whole thing up. You get a 0 if you reduce the wrong way. It is a sign of us differentiating between barely adult and children. You go and give a talk and you make the wrong reduction, immediately people walk away. Okay? Let me show you the first big creative jump. It turns out that this problem is NP complete. The K-clique problem. Well, what is the K-clique problem? The K-clique problem is the following. You are given a graph G and a number K. And you are asked, in this graph, is there a clique of size K? Once again, what is a clique? A clique is simply a bunch of nodes that are all connected to each other. So, here is a 3 clique and here is a 4 clique, and likewise I can do a fly clique. I think I have connected everybody. So, this is a 3 clique, 4 clique, 5, and so on and so forth. Now, you might say, why is this problem at all difficult? You look through the graph, you find a bunch of nodes that are all connected to each other. Unfortunately for you, these graphs are not given to you as a picture on a piece of paper. And in fact, if I took those nodes and put them everywhere in your graph, you would not be able to tell that they are all connected to each other. For the longest time, because we are doing all kinds of graph theoretic problems, we thought that this might be solvable. Somehow go and find out if you can find some group of 3 or so that essentially is connected to everybody. We could not find a polynomial time solution. We kept trying and trying and trying, we could not. Then it was shown that K-clique is actually NP complete. The problem is the following. I give you a graph, I give you a number K, and I ask you, is there, let us say K is 16, are there 16 nodes in this graph that are all connected to each other? Try it. We have spent 30 years. They have to be all connected to each other. You see, unless you try to find polynomial time solutions to these problems, you will never understand why these problems are turning out to be so difficult. Unfortunately for you, you have very little time between now and your final exam, but I really advise you that after the exam, when you are calmed down and everything is done, try to see whether you can come up with a polynomial time solutions to these problems. At the very least, you will find out why these problems are difficult, because if I just keep telling you that these problems are difficult, it doesn't mean anything. Okay? Soon as we show that the K-clique problem is NP complete, what we have really shown is that if you find a polynomial time solution to the K-clique problem, you have essentially found a polynomial time solution to all problems in NP. That is a huge thing. Therefore, it is very unlikely that you will find a polynomial time solution to the K-clique problem. But that is not a proof, it is very unlikely. But this whole idea of whether P is in NP or P is not NP is about finding these problems and realizing that a polynomial time solution to any one of these is a polynomial time solution to any of the other guys. So, we are expanding this group of problems that we have, and you can target the one that you feel very comfortable with. It does not matter whether you are comfortable with 3 CNF, you go do your 3 CNF. I am comfortable with K-clique, graph theoretic ideas, I go and do K-clique. What these theorems are showing is that a polynomial time solution to any one of them is a polynomial time solution to all the other people. So, it is not at all important which problem you target. Okay? But showing that the K-clique problem is NP complete is a different business. Yeah.
So it's exponential in terms of number of edges. Okay.
The size of the problem is the size of the graph G. So, you will be given an adjacency matrix or an adjacency list and a number k, and you will be asked, can you give me a polynomial time solution given this thing? Is the nature of the problem making sense? Now, when I am going to try to show that the K-clique problem is NP complete, I am not going to try to solve this problem in polynomial time. Okay? What I am trying to show is something completely different. So, tell me this, which one should I show? I will choose 3 CNF to be the one which has already been shown to be NP complete and therefore NP hard. And so, I am going to do a reduction with respect to 3 CNF. But tell me, should I do this? Or should I do this? How many think the first one? How many think the second one? Oh, very nice. You're okay. Which one? First one or second one? Okay, so let me again give you this quick way of reminding yourself what needs to be done. If you know that a problem is NP complete already, that is NP hard, draw in your head this picture. All NP goes to that problem. So, in this case 3 CNF. If I can show that, then I am showing all problems through this connection can be reduced to K-clique, which is what I am trying to show. Remind, always draw this picture in your head and you will immediately know which guy goes to which guy. So, 3 CNF to K-clique, this is the direction we have to go. We are essentially trying to show that K-clique is at least as difficult as 3 CNF. In other words, we are trying to show that you give me a 3 CNF, I will turn it into a K-clique. And I will show you that the K-clique solution, yes, no, corresponds to the 3 CNF solution as yes, no. So, if it turns out that you actually find a polynomial time solution to K-clique, this is what I will do. I will say that I have a polynomial time solution to 3 CNF. How do I do that? I take my 3 CNF, I hand it to you, you solve it, you give me the yes, no answer, I give you the yes, no answer, polynomial time. That is what reduction is. So, I am not trying to solve the 3 CNF problem, I am not trying to solve the K-clique problem, I am trying to show you that given any 3 CNF there exists a K-clique problem that has a correspondence in answers. But before that I have to do the simple thing. So, the K-clique has to be shown in NP. How can you show that the K-clique problem is in NP? Is it a decision problem? Of course, yes. But we need to show that it is verifiable in a polynomial time, by which we mean that we need a certificate and we need to show that we can use that certificate and verify. What will the certificate be? The nodes. You are already getting the hang of it. So, always do this first piece first. Your certificate is going to be the nodes, and it is very easy to say that okay, I am going to just go and make sure that each node is connected to each other node. It is going to take me polynomial time to just check this, and therefore, it is verifiable in polynomial time. Now, the difficult part, K-clique is NP hard, and to show K-clique is NP hard, we are going to do 3 CNF is reducible to K-clique. Take a moment, understand that this is completely out there. How am I going to take a Boolean formula which is on the left side and make it a graph theoretic thing? That is the creativity behind NP hardness proofs. On this side sits a Boolean formula. You give me a Boolean formula and I have to somehow take it and make it a graph theoretic formula. let us not do the stupid thing. The stupid thing is the following. I take the Boolean formula and find out whether it is satisfiable or not, and if it is satisfiable, then I give you a graph which has a k-clique, and I set k to be 3 and put a 3 node there, and if it is not satisfiable, then I make sure that no 3 nodes are connected to each other. Well, if you could do this, whether it is satisfiable or not satisfiable, we would not care about this game at all. So, any solution that starts by saying that if the answer is yes, and I find out that it is yes and then do this, you have lost the game. Without knowing the answer, you have to transform it. Without knowing the answer. So, I will just give you a formula, and you will look at that formula and say, I do not know whether it is satisfiable or not, but I will show you a way of turning it into a graph such that if the graph has the answer, yes, then this will be satisfiable. If the graph has the answer no, this will not be satisfiable. Is that making sense? Okay. So, here is how I go about doing it. Let us take let us assume that this is the thing that has been given to me. So, once again I am describing it to you as if I were given a 3CNF, and I am going to turn it into this, but what I am describing to you is a generic algorithm. I am just giving you the algorithm through an example so that you understand. Okay. So, when you are given a 3CNF formula, what you basically do is you set up 3 nodes per class. On some big circle, I am going to just set up 3 nodes per class. I then do the following, right. Within any set of 3 nodes, I am not going to have any edges between them. No edges between these groups of 3s. However, so I am going to assign x1 here, not x2 here, x3 here, that is x1, x2, and x3, that is not x1, not x2, not x3, and so on and so forth. If you have many more classes, you will have many more groups of 3. So, right now I just have 3 classes, I have 3 groups of 3. I then simply do the following. From x1, I go to any group and put lines out to every node except for nodes that say not x1. So, here I will go from x1 to x1. In this one, that is a not x1, I am not allowed to connect to that, I will connect to everybody else. Same thing here, I go to every class and put connections in except for the ones which says not of not x2, which is x2. So, I connect there, I do not connect there, I connect there. I connect there, not x2, I connect there, and so on and so forth. And I do all these connections for all the nodes. This is going to be my graph G, and the number k I am going to give is the number of classes. So, in this particular case, k will be equal to 3 because I have 3 classes. And I claim now that a k-clique in this corresponds to this formula being satisfiable, and the non-existence of a k-clique in there corresponds to this not being satisfiable. So, I am going to show if this is satisfiable, there exists a k-clique, and if this is not satisfiable, there does not exist a k-clique. Right? A implies B is the same as not B implies not A. So, you can go about it any which way. Look at how beautifully this thing has been done. If this thing has a k-clique, in this particular case a 3-clique because there are 3 clauses, can you see that one node will come from each one of these groups? You cannot have 2 nodes come from a single group because they are not connected. So, if this one has a k-clique, it immediately means that you get 1 node from each group. Those nodes will never have edges going to nodes. So, you will never pick up 2 nodes where you pick a x1 here and you pick a not x1 there. It is not possible because I did not put that edge in. So, this essentially means that if I go and choose these particular nodes and turn them all on in each class, it will be a perfectly valid assignment and it will make that thing go 1. So, I have shown you that if there is a k clique, then this is satisfiable. I have to show you that if it is satisfiable, there exists a k clique. This other way is also very easy. If it is satisfiable, there is a assignment here such that one or more in each class is turned to 1. Just pick those nodes, just one from each class, and choose that node in each group. Once again, based on the way I constructed the whole thing, it will turn out to be a k clique, because you will have one node per group. You will have as many clauses as number of nodes, that is k, and we know that it is going to be a clique because of the way I have put the edges in. I have neither tried to solve this problem nor have I tried to solve that problem. All I did was a construction that turned one problem into another problem. To some people, this kind of thinking is relatively difficult. But this is a proof that k clique is NP complete. We will stop here. I will come back. I will make sure that you get a good sense of exactly what is happening. Maybe I will try another problem and then give you the high level view of how Cook went about proving his thing. Okay? And then we will have the semester end.